went to Texas a few summers ago, and it started raining, and there was like 3 or 4 accidents on the highway that I was on. And I watched the news, and it just said people weren't used to any rain at all. So
rain?
They weren't used to it being slick at all or anything.
They freaked out.
Yeah.
Ah, well. So your textbook points out that all sorts of people care about the weather, including folks that are trying to get things in orbit. We care about the weather, severe weather, and, you know, it just makes a difference. It's more than, actually, I just look in the morning so I know what to wear. So I've got a flow chart to kind of show how this is all organized in a minute. But, of course, you've heard of NOAA. That stands for National Oceanic and Atmospheric Administration. But there's all sorts of things under NOAA. So there's also the National Environmental Satellite Data and Information Services. There you go. Never heard of those guys before. Of course, you've heard of National Weather Service, NWS, but have you heard of the National Center for Environmental Prediction? And actually, there's several organizations under the NCEP. So the National Weather Service and other organizations you're going to see, they have various ways of figuring out what the weather's going to be, of coming up with a weather forecast. And we'll talk about those. But once a weather forecast has been thought up or come up with, then of course it needs to be disseminated, and that comes down to the local offices and the private sector. So this is new to this edition, I think. I think this is pretty darn good. This is one to kind of help sort things out. So there's NOAA. Okay. I used to think NOAA was underneath NASA, but I looked it up and couldn't really find the direct link. Of course, they work close together when it comes to time for satellites and that sort of thing. But NOAA has your National Weather Service, and then these are the data guys. Okay, so under the National Weather Service is a bunch of stuff. We have the folks that are coming up with forecasts, the regional offices, that's like the Quad Cities, that sort of thing. So under people who are coming up with forecasts, we have people working on climate prediction, environmental modeling, Weather Prediction Center, National Hurricane Center, Storm Prediction Center. We talked about these two in the previous 2 chapters. So they're all under the NCEP, which is under the National Weather Service. So when we, though, coordinate with folks in the National Weather Service, the local offices, that would be reflected right there. So a career in meteorology sounds like a good idea. Some of these things you may or may not have thought about. One of the things, and I think I might have mentioned, I guess, this to my other group, you can almost tell when a meteorologist has got the whole science thing. You know, the meteorologist, I think of as like on the TV, like this guy, okay? You want to be good at your job, I think you want to be explaining things in a scientific way, but so the public can understand. Notice that there are lots of people going behind the scenes, okay? Research, teaching, broadcasting, private sector, with specialized clients. National Weather Service, of course, would be a potential employer. Folks in aviation, military, NASA. The ongoing research is associated with this organization, the National Center for Atmospheric Research in Boulder, Colorado. Now, the difference between a meteorologist and a climatologist, it almost sounds like from your textbook that a climatologist is kind of an offshoot. First you become a meteorologist, and you may or may not become a climatologist. That actually, climates is like a 30-year average of the condition of the atmosphere. So, in the movie The Day After Tomorrow, one of the heroes was a climatologist, Jack, I think. So at the beginning of most forecasts, we need to have some solid, what we call current or initial conditions of the atmosphere. Oh yeah, I kind of got ahead of myself. So, and we need to know the conditions of the atmosphere worldwide. There's something called the butterfly effect, which basically says if a butterfly flaps its wings down here in South America, it can disturb the atmosphere, so it actually has consequences to our weather up here, the butterfly effect. So this whole what's the condition of the atmosphere is really kind of important. It's kind of neat because this World Meteorological Organization is plugged in to folks that are members of the United Nations. And then there's 3 World Meteorological Centers, and one of them is in the United States. And notice that our center is coordinated, not so surprisingly, by the National Weather Service, more specifically the National Center for Environmental Prediction. Then we have one in Russia and then one in Australia. So those 3 kind of centers then kind of disseminate the world information from that point. All right. So throughout this chapter, we need to talk about how do we get these initial conditions that we're actually going to use in our forecasts. So some initial conditions are gotten directly, some are indirectly. So we've talked about the ASOSs, right? Remember this, ASOS? This is an ASOS. We talked about that before. They're great. They can actually automatically measure a bunch of stuff. We said they're usually located near airports. Your textbook says that these automated surface observing systems, they're not quite as good as the human being sometimes. But that's just the United States. And worldwide, I think this is kind of cool. Worldwide, there are actually 11,000 sites where initial conditions on the surface are being gathered. Ships 4,000, those data buoys 12,000, or excuse me, 1,200. So those were surface, okay? I want to distinguish that from upper elevation. What is the atmosphere doing above the Earth's surface? And that's very important. We talked, you probably already have a sense for kind of the exchange of what's happening in a loft has an impact on what's happening at the Earth's surface. So one of the things to get a sense for what the conditions of the atmosphere are up at upper elevations is to send up those weather balloons. We kind of talked about that. Remember, here in the United States, they're sent up twice a day. Notice that there are 1,300 stations that send up weather balloons across the world. 92 are in the United States. And we talked about the balloon will get larger and larger and larger, the size of a house, and it will burst. It takes about 2 hours to go up, and hopefully its parachute opens and it can come back down. I wonder if they ever run into an issue where somebody gets hit by one of those things falling down. Never hear about it, you know? There's a subtle difference between boxes that go up in a weather balloon. Kind of the normal one is a radio sound, and it gives us stuff like pressure, temperature, dew point temperature. And then there's the raw sound, and I think that's kind of the special one. And it gives us information about the wind, speed, and direction. And your textbook says that when these radio sound or raw sound goes up, they're actually sending information probably back to one of the National Weather Service offices. So there's even more ways to get, other than a weather balloon, to understand the conditions of the atmosphere up at upper elevations. One is airplanes. They just actually, as they go about their business, are equipped to send back information about temperature and airflow. Satellites, we'll talk a little more about satellites coming up, but satellites, of course, are orbiting the Earth. This would definitely be an indirect method of getting atmospheric conditions. Wind profilers are a type of radar where it sends out a signal, okay, but in this case, it is actually getting back information about the wind, direction and speed. And then we already talked about Doppler radar. And so, but we can take Doppler radar and get a sense for what's happening in upper elevations. Cool. So the term synoptic weather map, okay, is synoptic weather map is the snapshot of what the atmosphere is right now. It's not a forecast. It's a what is it right now. And all those things I listed before about getting conditions of the atmosphere, those would be fair game in putting together these synoptic maps. Historically, they used to be drawn by hand, but now it's a lot easier. Okay. Now, synoptic maps aren't just at the surface, they are at different elevations of the atmosphere. Okay. So I have I don't know if you can read this very well, it's kind of hard to see, but where would you draw the front line? And actually, I should have had builds here. So that's the raw data. We talked earlier about this idea of a station model, and I'm thinking that it is like worldwide. It's kind of nice because you don't have to speak the same language to understand a station model. What we've been really using a station model for, I know there's a bunch of word numbers on here, but this is the current temperature, and let's see, this is the dew point temperature, 34, 32. We've been using those a lot. But your models can get quite complicated. So this little icon tells us where, what's going on. So let's take a look. You know, one of the things with synoptic maps is you should be able to draw fronts. So they're saying, for instance, this is a cold front. Oops, this is a cold front right here. So let's see, I got 47 and I got 67. I'd say it's a pretty good place to draw the front. So here's a couple of synoptic maps. Now these are different. The one there over on the right is kind of a what we call a mixed surface map. And you know it's mixed because the greens and the yellows and the reds, that's actually precipitation. That comes from radar. This one over here on the right, did I say it right? That's left, it's the surface map. Over here on the right, it's actually at upper elevations. Now, I'm going to remind you how this works. All right, those look like isobars, but they're actually iso heights. And this actually, these are iso heights that you need to go to get a pressure of 500 millibars. In general, here at the Earth's surface, even though it varies a lot, we run about 1,013 millibars. So 500 millibars is at upper elevations. Iso heights, though, work just like isobars. The closer they are together, iso heights are together, on an isobaric chart, the faster the wind is. These are at upper elevations. All right, so these are synoptic maps, kind of a snapshot of what the atmosphere is at that particular time. So that was 500 millibars. Now this is 850 millibars. Now think of what that means. So I need to get to an elevation where I have 850 millibars of pressure. So does this make sense? These are closer actually to the surface than the 500 millibars. Okay. So these are, I guess, also synoptic maps. And your author's gone ahead and drawn in, we talked about air masses, so this is kind of exciting. That actually, does this look like a cold air mass pushing in, and this is a warm air mass moving up? And we talked earlier about kind of the troughs and the crests, okay? And we said lows are associated with troughs and highs are associated with crests. Here's our low. Okay, we don't have the high up there, but it's probably hiding. Oops. Did you guys need that one? Okay. So 850 millibars is closer to the surface than a 500 millibars isobaric map. So back to the 500 millibar isobaric map, and this actually kind of looks like the same. You can compare them back and forth if you want, but it's the same time. So we're going up in elevation compared to 850. We can use this to anticipate kind of some steering that our mid-latitude cyclone might undergo. And then we go to 200 millibars isobaric map. Now, 200 millibar isobaric map means you basically kind of have just 200 millibars of pressure versus 1,013 millibars of pressure. So this is the upper elevation. At this point, we can actually see that ribbon of fast-moving air, the polar jet that is between the Ferrel and the polar cell. The last note up there says that if we have significant, if the winds pick up quickly going up, actually that can be a player for giving us wind shear that can make our thunderstorms last longer. Wind shear, remember that's the tilted versus the majestic. Okay, so kind of along those lines, just keep in mind that the polar jet stream, if the jet stream is relatively strong, that will give us wind shear that will strengthen our TS. Here stands for thunderstorms. TS is thunderstorms, not tropical storms. So our thunderstorms will intensify, last longer, and actually strong jet streams play havoc with our hurricanes, and so our hurricanes are less intense or less likely to be. And if the jet streams are weak, then that will strengthen the hurricane activity, and it will weaken our thunderstorms. All right, called numerical weather forecasting. Numerical weather forecasting, numerical weather prediction, it's the same thing. And at the base of this, we use a computer, and basically what scientists have done to the computer is that they have prepared programs that are in the computer ready to receive initial conditions. Okay. So those programs are called models, and there are various models that work well for different regions of the world. And for the same region of the world, you can have different models. You get to pick your model. So then what happens is, once you picked your model, or models, you go ahead and feed it. You feed it initial conditions. So I went ahead and went out on, this is WeatherSpark, so if you just type in WeatherSpark, it's like Weather Underground, okay, but it's got some cool features. So go ahead and we'll put in our zip code. It's kind of pretty, you know, it's kind of busy, all sorts of things to kind of play around with. I think WeatherSpark is one that we might pull up when we look at climates. But if I go to forecasts, this is what I want to show you. If you go to forecasts, and I know there's other apps that do this, but do you see the NOAA? Okay, this one right here is Norwegian Meteorological Institute. This one right here is World Weather Online. So these are actually different models. So take a look at, tonight's forecast says clear to mostly clear. And if I go to this one, it just says clear. Notice here it says tomorrow temperature range is going to be 72 to 48. Oh, that's nice. If I go to this middle model, okay, it says it's going to be 73 to 47. So they're just different models And it's amazing this day and age where we can go ahead and just pick it, you know? So, and we're going to be looking at accuracy, forecast accuracy coming up. Okay, so those models accept a bunch of data. Now that's probably one of the problems with numerical weather prediction, numerical weather forecasting. That's a heck of a lot of data to take in. So just to kind of talk you through what happens when the data meets the program, when the data meets the model. Well, your textbook doesn't really talk about this smoothing process, but if you've ever done much with numbers in a lab, you know that sometimes you throw out outliers, you know, things that don't make sense, you kind of weed it out. There's a little bit of that, and there's also a little bit of smoothing. Like if you're missing a data point, you can actually go ahead and kind of arch something in between. Go ahead and feed your model. Okay, so that's kind of called smoothing. So then what happens is whatever model that you picked is going to take that data and run with it. But it won't run very far. And like this example here is about 2 minutes. So basically, it will do a bunch of calculations and spit out the forecast for 2 minutes from now. You're like, well, that's not going to help me. But then it basically takes whatever it got, and it says, oh, those are going to be my new initial conditions for 2 minutes from now. And it takes those, and it plugs them back into the same model. And now it spits out 4 minutes from now. And it takes those, plugs it back into the same model. Now it's going to spit out 6 minutes from now. And does it very fast. But that's a lot of, that's three-dimensional, that's a lot of stuff. So that's how it kind of crunches those numbers. So, like I said, that's a lot of crunching. And the concept of using like a mathematical model to receive initial conditions, that came up way before computers. And so it wasn't until computers came along that someone was like, oh my gosh, we're so going to use a computer for this. Something about, I read, it was when they came up with the model idea and the initial conditions, you could go ahead and calculate a forecast for tomorrow, but it would take you 7 days to do it. So it's like, So anyway, so kind of that initial what the computer says is the forecast. Those are called prognostic charts, or progs. So that comes from the computer. Well, computers are not infallible, and computers need humans. And that's where this model output statistics come in. I bet this is humans that are using their own common sense, okay, to kind of tame down or beef up where it needs to be. So model output statistics would come after the progs, or the prognostic charts. So, you know, how could you go wrong with the computer spitting out something and you kind of tweak it? Well, I already told you the third one. It just takes, that's a lot of computing power. But honestly, the first one, the thing about the models, we do our best to come up with models, and you can see there's kind of an assortment of models out there. But you can't really, nature kind of does its own thing to a certain extent at times. And then the middle one right there, you figure if you're feeding it like all of this initial conditions, what if somebody gives you some bad data? Okay, then you're potentially screwed. So those are kind of three things that are kind of make it difficult. So here's a typical prog, or prognostic chart that the computer spit out. Not bad. This was prepared, looks like I missed a 0 on July 27, 2014. The National Center for Environmental Prediction. Okay. So I already mentioned what the butterfly effect is, okay? what I say here is basically, if you tweak, if you have a slightly different initial conditions and you run it through your model, you're going to get something potentially way different, because that small change is aggravated when you take it through your model. And that's similar to the chaos effect. The chaos effect is inherent in everything, in all the sciences. Chaos is here to stay. But it also says that just if you have slightly different initial conditions, you're going to get a significantly different forecast. So what do I mean by slightly different? So here's the deal. If we just take temperature, just take one temperature. Anytime you make any measurement, there's a plus or minus. And that plus or minus is the tolerance, and it's related to your thermometer, and sometimes it's related to the person reading the thermometer. Thermometers are harder to read than you think sometimes. So let's just say you went 32, and your tolerance was 2 degrees. So it could actually be 30, 31, 32, 33, or 34 degrees Fahrenheit. So which one do you feed? Well, you go with 32, but it really could be any of those others, okay? And that's the problem. That's what we're faced with. So this is one way to fight or combat this kind of the butterfly effect, the effect of chaos. It's called ensemble forecasting, and we're going to see. We talked about numerical forecasting, using initial conditions and computer models. We're going to have some other kind of general forecasting, and ensemble forecasting is one of them. So basically what you do is you feed your model and your initial conditions, but you go ahead and kind of understand the tolerance or the uncertainty of your initial conditions, and you feed it slightly different initial conditions based upon what you know. So in the case with the temperature, we would feed it 30 degrees Fahrenheit, we'd feed it 32 degrees Fahrenheit, we'd feed it 34 degrees Fahrenheit. And we come up with 3 different outcomes, possibly. And I'm going to show you an example of this. So in ensemble forecasting, then, you basically end up with a whole suite. The word ensemble is, if you play in a musical ensemble, then you have a lot of people, with you. And so you end up with like a whole suite of possible forecasts. And so what you do is you look for patterns. So here we go. The example that I've got here, so it's all going to come up at once here. Yeah. So I'm going to show you, I guess, if you live in Europe, this might have been one of those days that you kind of remember the weather went wacko. Notice it is Christmas Eve, and they misjudged it. The folks here in Germany and France got hammered with a mid-latitude cyclone, I think, and that's not the forecast that they gave them. So I'm going to show you that in this particular case, like hindsight is 20/20, if you could go ahead and put together a suite or use this ensemble approach and come up with a whole bunch of different weather forecasts, you would see a pattern. And you would say, you guys might want to be prepared to be hammered. Okay? So here we go. Looks like this. Let's see if we can kind of do better than they did. Again, hindsight is 40/40. Hindsight is 20/20. So this is what they forecasted. Those lines there are isobars. So of course the isobars are not too close together. So what they forecasted was, don't worry about precipitation, not much anyway. Okay, and then this is actually what happened. So of course you can kind of see we definitely right here, had a situation. You kind of see the bullseye. Okay, that is like the intense precipitation that they got. So all of these forecasts, 1 through 50, are initial conditions just slightly different. So if we go along and kind of, let's see, what color do I want to choose? If we go along and kind of circle where we see kind of this pattern of a mid-latitude cyclone, you know, in that region, you know, it's definitely on the radar, no pun intended. So, I don't know. Like I said, hindsight is 20/20. These are gonna. Well, that's a good place to break. So we'll take a break, and we definitely won't be here the whole time, but kind of want to break.